Hi there, and welcome back to our exploration of the internals of relational database systems, namely PostgreSQL and MongoDB. Hi, welcome back. This is already the first video for chapter 4 of the course, so we are really making some progress here. Earlier, I promised that we would zoom further into the details of how a single row is represented, and that's exactly what we are going to do now. A row is actually a simple thing, just a sequence of fields, you would think, but internally the system makes some quite interesting design decisions when it comes to the representation of fields, their order, how null values are represented or not represented, and so on. And that's the topic of the next few videos. Okay, so row internals. Let's see. Of course, we will use a probe query again to explore what really happens behind the scenes. And that's what we're doing here. So another probe query, Q3, is on the table now. This is Q3, and you see that it's still querying our 3-column ternary table with columns A, B, C. But this time, we are only requesting the fields A and C here. You see that the column TB has been projected away, as the database folks would call this operation. So retrieve all rows, but we have to unpack, or we have to navigate inside the row T to see that we can only extract the fields A and C and somehow skip or ignore or project away the B field. Okay. So this is our column, our table ternary, as you recall. This is the 4-byte integer column called A. This is a variable width text column B, and an 8-byte floating point column C here. And you see that we are admitting null values at this particular point, and this will come important in a minute. Okay. Let's create the table. Let's create the table on the PostgreSQL side. So here's a spurious tilde sign. Here's our DDL statement for the creation of the ternary table. Let's do that. Okay, here we go. And you see that I've added some comments here that indicate the byte width of the respective fields, and this will become important in a few moments. Okay, so let's now populate the ternary table again with 1000 rows. That's what we're doing here. The A and B columns are populated as before, so with just an integer and a 32-byte text string here, and we still save logarithm values in column C, but every 10th row, in every 10th row, we will place a null value instead. So whenever this I here is divisible by 10 without any remainder, okay, then we are placing a null value. Otherwise, we will just place the usual logarithm value there. Okay, so column C will indeed carry some null values. Let's do that and fill in the values. That's what we did here. Insert 1000 values. Make sure that the system is up to date about the internals of the system. Okay, and then we could just fire the probe query Q3. Let's see what happens here. So it's a 2-column table. The textual column B is missing, and you can see that in the C column, in every 10th row, we indeed find a null value. So there must be a null value here somewhere. It's here. Okay, so this is the layout of our ternary table now. This is the playground we are using to do our stuff. Okay. So then initiate the database X-ray, the database system X-ray again, and use explain on the query Q3. And we can do this in the terminal in a minute, but this is what we are going to see. We are going to see a sequential scan again, because the query is super simple still. And of course it will hit the ternary table, and of course it will only return two columns, the two columns A and C here. And because the resulting columns are narrower, the width of the emitted rows is being computed as being 12 bytes wide. 12 bytes wide, this corresponds to the 4 bytes of the integer in column A and the 8 byte of the float in column C. Those two add up to a row width, average row width of 12 bytes. In this particular case, we are projecting away the B column. The resulting rows are narrower. Okay. If you recall the cost estimate that PostgreSQL was assigning to the evaluation of our probe query Q2, Q2 was not projecting away the B field. Query Q2 was returning all three columns A, B, C. So, and you would expect such a query to be costlier, or to be estimated costlier than a query that may omit the B field here. But if you recall, the cost estimate for the Q2 query indeed has been the same. The system estimated a cost value, whatever that means. It's not seconds or milliseconds or something, so be aware of that. It's just an abstract cost value. And the system for Q2 estimated the very same cost value. And the reason for that is in the row storage of the PostgreSQL system. Recall that PostgreSQL would access entire 8K blocks on which the fields of each row are held in contiguous memory. So accessing the rows of table ternary will always bring into RAM the fields A, the fields B, the fields C, all the fields of such a row because they're in contiguous memory inside the 8 kilobyte page. Later, when we then further process the query, we will see that the B fields have been brought in from disk in vain and are not actually needed. But they contribute to the cost of bringing data in from disk into RAM. And so we cannot gain much in this row storage system by ignoring the field B here. In fact, we will pay dearly for the extraction of A and C and the skipping of B, as we will see later on. Okay, so this is what we are observing regarding the plan, a sequential scan that omits a field. And omitting such a field, so extracting only A and C and omitting B, this of course requires a navigation of the row T and the extraction of the wanted fields. And to understand how this goes on, we have to zoom. We have to zoom inside a single PostgreSQL row, and this is what this slide tries to explain. This would be the entire PostgreSQL row. All right. As we learned in the last videos, such a row consists of a row header of at least 24 bytes, as you can see, and some payload data, the real column data that we've stored inside the table. So there's a row header here that contains some meta information about the row and that helps us to navigate the row. There's a fixed piece of header in the very beginning here that's used to store the row ID, that's used to store some meta information for transaction management, for parallel access to such rows, and that's always in place and it will always be there. But then there is some component in the row header that is of variable width, the so-called null bitmap, which we will talk about later. But this bitmap is of variable width. For very wide rows, the null bitmaps are wide. For very narrow rows, null bitmaps are very narrow, and they may even be omitted entirely. So this is a variable width part of the row header, and because of this, you will find in these row headers, you will find an offset field. We have already seen that as we were listing the heap page items in an earlier video. And this offset tells the system that the actual payload column data begins at offset t_h offset. Okay, so normally that would be 24 here if the null bitmap is not too wide, but this is in fact a row internal pointer that points us to the actual column data here. All right. Okay, and then if we would look at this column data here, we would see that some of the bytes, most of the bytes hopefully, are actually occupied with payload data, with integers, with floats, with characters that we have stored in the columns. But there's also some so-called padding bytes that we will come to in a minute. These padding bytes are there to make sure that the actual payload data, for example, this piece, is located in memory at an address that a modern CPU can actually efficiently access. So sometimes there is some additional data that we might not be expecting here that will lead to a payload data that is wider than actually the data types in the columns would suggest. All right. Note that the output of our DBMS X-ray of explain, when it reports the width of the row, the width W of a row, it only accounts for the raw payload data, for the dark gray pieces. It does not account for the padding data here. Despite these padding bytes really being physically present on the page and really occupying some space. So this width output of the explain command is really a sort of underestimation of the actual bytes that are needed to store the bytes of a row. So let's look at this padding and the organization of the payload data some more. So this again would be the entire row. I have now omitted the metadata, the header information that is present in the row, and I've only focused on the actual payload data. And for a row in the ternary table, we know that the payload data has to have 3 sections, the A, B, and C column sections. The A column section would actually start at offset 24 as being indicated by T_H offset. Okay, and this will occupy 4 bytes for a 4-byte integer. Then we would have the part that stores the characters of the column B, of the textual column B. Okay, this would start at offset 28. And actually, this is the point where this textual data would be complete already, and we could now store the bytes for the column C, for the 8-byte floating point column. But alignment requirements of modern CPUs and memory subsystems require us to store an 8-byte value at an address that is divisible by 8 without remainder. So in general, an n-byte value, a value of width n bytes, for example, an 8-byte floating point value, has to be stored at an address A, which is divisible by n without remainder. So this is the requirement that we are seeing. Okay, so this 8-byte floating point value, the contents of column C, has to start at an offset inside the row that is divisible by 8, and the next offset that is available that would be divisible by 8 without remainder is the offset 64, and we are ending up with some padding bytes that don't carry any useful information but are only there to support the efficient and the correct access of this 8-byte value at this particular offset. You see this mentioned here in the footnote on the slides. Modern CPUs and memory subsystems have these requirements to either efficiently support the access to values that are wider than 1 byte, or to even support such access at all. There are even CPUs that would throw an exception that would regard it as a violation to access such a wide value at an address that is not divisible by the byte width. Okay, so this is the reason for these padding bytes. What about the padding requirements for the different data types in PostgreSQL? We can ask the PostgreSQL catalog to reveal that. So let's switch back to the terminal here. And you see this is the query that asks the PG underscore attribute table for some information. PG underscore attribute is part of PostgreSQL systems catalog. And inside that table, we can find information about attribute position in a table, attribute names, how many bytes are actually required to store a particular column or attribute, and where that attribute would be stored inside the page or maybe even outside the page, and what the alignment requirements are of that particular column or attribute. Okay, so we are doing just that for the ternary table now, and we only outputting information about the real user-defined columns. Each table has system-defined columns that we are not interested in here. One such system-defined virtual column would be the CTID or the RID column. This predicate here will make sure we are only seeing the A, B, C columns that we have defined. Okay, so let's fire up this query. All right, this is the result. Of course, we get 3 resulting rows because there are 3 columns, 3 attributes in table ternary. They are at positions 1, 2, 3, and they are named ABC. We've known that already. A is a 4-byte integer column, and we can see that. C is an 8-byte floating point column, and we can see that. B is the variable width column, and the actual width of that is unknown. It might differ from row to row. That's why we see a -1 here, which is an indicator that the width may actually be varying. Add storage with P means the value of this particular attribute, of the A and C attribute, for example, will always be stored inline inside the row, inside the 8 kilobyte block that the row itself is living on. X means that such a value might live on this particular page. It might also live on an external page if that particular text value, for example, is just too big to live on that page. That's a feature of PostgreSQL that's called toasting. Nice name. We will come to this in the lecture later on. All right. But of particular interest are now these attribute alignment information columns. Okay, and we see that the alignment requirement for a 4-byte integer is that of a normal integer, a 4-byte integer inside the CPU. The alignment requirements for an 8-byte floating point value are that of a double width word. So in this case, it's an 8-byte word for this particular CPU. And the alignment requirement of a float require us to have an alignment that is compatible with double width words. So in this machine, 8-byte words, and that means we need quite some padding, namely addresses that are divisible by 8 without remainder. Okay, so padding can be substantial. And I would like to take a few minutes to really try to quantify what padding can mean for such a table. Okay, so what we could do is play some column Tetris in a way. We could create 2 tables, 2 equivalent tables. Let's call them padded and packed. And padded and packed have the same number of columns, namely 6 columns each, as you can see, and each of these columns would carry the same data types. I'm very specific about the data types I want to store in these columns. As you can see, PostgreSQL not only has the integer data type, but also special integer data types in which I can specify how many bytes should be occupied by this particular integer. So int2 occupies 2 bytes. It's a 16-byte integer with values ranging up to 2 to the power of 15 minus 1 in 2's complement representation. But that's not no issue here. It's about the 2 bytes that this type will occupy. And of course, as you can imagine, this int8 type will occupy 8 bytes. So this is a wild mixture of columns that would need 2 or 8 bytes to represent their column values. And the padding requirements for an integer 8 are indeed that it has to be stored as the double word in an address that is divisible by 8 without remainder. So some very strict padding requirements here. The padding requirements for a 16-bit word are only that they are stored at even addresses. So, okay. So the same columns, but in different order, are stored in this packed table. All right. And as you can see, I have been somewhat clever here and have organized all these 8-byte values, these integer 8s at the beginning of the row. So a B can follow A without any padding. If A is aligned, then B will automatically align, namely 8 bytes later in memory. C will be automatically aligned, and D, E, F, they have no problem at all. They will be stored at even addresses, tightly packed just after the C column here. So that's fine. It's not so great in the padded table, where the required padding will add our space requirements up to overall 48 bytes. 48 bytes. It's only 30 bytes for the same information here in this Tetris column organized packed table, in which we save all the padding requirements. We will see that this table only requires 30 bytes for its rows. Actually, it's a bit more, it's 32 bytes, because there's some internal requirement by PostgreSQL that a row may only start at may only start at offsets that are divisible by 8. 30 is not divisible by 8 without reminder. 32 is, so we lose some space here, but 32 still is way better than 48 bytes for the same information. Okay. This might not look much here. So 48 bytes, 32 bytes, what's the difference here? But the difference becomes relevant when we look at tables that are of significant width. Okay, so let's do that. Let's switch over and play column Tetris in the system over here. Okay, so I will do just that. I will create the padded and the packed tables as shown on the slide, and you will see that they indeed both have 6 columns and that they carry the same information, just that the columns have been arranged in different order. So let's create these 2 tables. Okay, then we will insert a significant number of rows here. You see that I will now insert 1 million rows. 1 million rows. Some of the column values will be set to 0, some of them will be set to I. That's not really super relevant here. I only make sure that I will insert the very same information, the same number of rows, of course the same number of column values here into the padded table and into the packed table. Okay, so let's insert rows into the padded table. It might take some time, I guess 5 seconds or something. Let's see. Time passes. 8 seconds. Okay. And now into the packed table. Okay. So both tables have been populated. So let's see whether we can really see a difference here, whether it makes a difference. We could, for example, in the beginning check how many pages are occupied by the padded and packed tables. And we would expect a packed table, hopefully, to occupy less space and thus maybe even less pages on secondary memory on disk. So let's bring the free space management up to speed here with what has just happened in the shell. Okay. And then let's check how many pages are actually occupied by the padded table. Okay, so you know the PG free space function. It's part of the free space management of PostgreSQL. I'm not interested in the actual free space bytes that are reported per page here. I'm just counting how many pages are being reported for the padded table. Let's see. Okay, so 9,346 pages. That's quite some pages already for the information in the padded table. Let's see what the packed table brings. Okay, That's less pages. Less pages already to store the same information in the packed table as for the padded table. It's actually only 79% of the space needed in the packed table as compared to the padded table. So there's already some space savings going on here. Let's dig a bit deeper and look at one particular page, the page 0 of the padded table as well as the packed table. So let's look at the padded table first, and then let's check how many rows actually fit on one page of page 0, on page 0, for example, in the padded table. Okay, there you go. So this is the fully packed page 0 of the padded table, and it can hold 107 rows, I guess. 107 rows have been placed on page 0 of the padded table. So let's see how things stand in the packed table. Okay, so 136 rows already. So more information in the same page space in the same 8 kilobyte blocks. Okay, let's look at some of the other fields here. So let's scroll to the top so you can see this table header. All right, so the T_H offset field, so the size of the page of the row header is 24 bytes in this case, and it's also 24 bytes in the padded table. So this is not where the savings come from. The saving comes from the more compact representation of the payload data. And indeed, the overall row size is only 54 bytes in the packed table. That's the 24 bytes that we have for the page header, and then another 30 bytes for the really tightly packed 6 columns of the packed table. Okay, and it's 72 bytes here. It's 72 bytes overall size for the padded table. So that's 24 plus 48 makes 72. So that is more space that is needed to represent the same information. So if you're really fighting for the last bytes and maybe even for the last bits of performance in the very last stages of your development of tables, maybe it makes sense to look whether column Tetris could be played, and the rearrangement of rows can save you some bytes here and there. As I told you, it may not seem much, but the number of rows, it's only 1 million rows in these two tables that we've just created, really can make a difference here. It's the factor, it's a multiplicator that multiplies all the space savings that we can obtain in a single row, and this might add up to something benefit. So finally, let's see whether the system thinks that it can save time or derive benefit from the fact that we have a padded or a nicely packed table. So let's see how the system judges or estimates the cost for query processing when it scans over a padded table or the packed table. And we use the explain verbs again to do this, just that. So this is the output for the padded table. This is the output for the packed table. All right. First, you can see two lies here. The system, the explain, promises that the width of the retrieved payloads is 30 bytes in both cases. This is for the padded table. This is for the packed table. And as we have seen, this is just not true. There is padding going on. And this padding appears to be disregarded for the padded table case. So, okay. Caught you there, PostgreSQL, with your lie about the actual row width. Okay, but PostgreSQL sees that the padded table, to scan the padded table actually will cost more than to scan the tightly packed table that is occupying less pages. You see that the cost of scanning the larger padded table is being estimated as 19,346 cost units, space, dollars, whatever. arbitrary abstract cost units, and it's only 17353 for the packed table with no padding. Okay, so the system estimates that it can really save some time here, and it's actually the case that the system can spend less time on, or will spend less time on when it reads the packed table, because it has to move and touch fewer pages on disk, heap file pages. Okay, so much for our first look into the internals of a PostgreSQL row, and the row header, the row payload, the bitmap, and the t_h offset field. We will meet these again in the next video, but also some interesting insight into the padding that is going on, and that contributes to the overall width and space requirements of such a PostgreSQL row. Okay, much more to be said in this particular department, but not in this video. It's long enough already, so let's call it a day, and see you next time. Bye bye.